Hey everyone, welcome to today's Explainer. We are going to jump right in and uncover the hidden mechanisms and really the invisible chemical detectives that are constantly working behind the scenes to keep our daily lives safe.
So here's a question we almost never actually ask ourselves. When you drink a glass of tap water, eat a piece of chicken, or take a prescription medication, you just kind of trust that it's safe, right? You assume it's free of toxins and that it is exactly what the label says it is. Well, the answer to how we can possess that level of absolute trust relies on the fascinating and largely unseen world of instrumental methods of analysis.
To understand exactly how this works, we're going to open 4 specific case files today: food safety and antibiotics, pure medicines and pharmacy, tracing environmental pollutants, and monitoring chemotherapy. Let's get into it. Because of the extremely wide field of application here, these sophisticated instruments act as the ultimate hidden detectives across almost all major sectors. I mean, we're talking everything from raw materials in the chemical industry to the precise biochemical makeup of human fluids. Analytical chemistry is basically the science of establishing the exact chemical composition of materials, whether they're natural or man-made. And these instruments provide the incredibly low detection limits that we absolutely require to guarantee our modern safety standards. Now, take a look at this dense, mountainous 3D chromatogram. These are the actual chemical fingerprints analysts use to separate and identify hidden compounds. By measuring the time it takes for different molecules to pass through a system while simultaneously tracking how they absorb light at various wavelengths, scientists can map out and literally isolate invisible, potentially dangerous molecules from a really complex mixture. It's like finding a needle in a haystack, but on a molecular level. All right, moving to Case File 1, Food Safety and Antibiotics, specifically screening for antibiotic drugs in food of animal origin. When it comes to agricultural and consumer protection, you know the food industry doesn't just operate on the honor system. It has incredibly stringent requirements backed by strict legislation to monitor permitted levels of contaminants. One of the absolute most critical applications of instrumental analysis is screening for antibiotic drugs in animal-based foods. We use these chemicals to keep livestock healthy, sure, but we absolutely do not want those powerful drugs ending up in our milk or our steaks. Instrumental chromatography acts as the gatekeeper here, ensuring our meat and dairy products don't contain any dangerous hidden residues of antibiotics that were meant solely for treating animals. Next up, Case File 2, Pure Medicines and Pharmacy. We are looking at the optical purity control of therapeutic molecules. So, here's the thing about the drugs we take. Simply having the right chemical formula isn't always enough to guarantee safety. In chemistry, some molecules have what we call enantiomers. Think of them kind of like your right and left hands. They are perfect mirror images of each other, containing the exact same atoms, but they cannot be perfectly superimposed on top of each other. In the human body, this geometric difference is massive. We have to separate these mirrored versions of a drug, because quite often, one version heals you, while the opposite mirrored version causes severe, harmful side effects. It's literally a matter of life and death. To solve this crazy mirror image mystery, our detective instruments use techniques like micellar electrokinetic capillary chromatography. Okay, I know, it's a mouthful, so we just call it MEKC. Analysts actually add specialized chemicals like cyclodextrins right into the testing fluid. These cyclodextrins act like microscopic traps. Even though the left-handed and right-handed drug molecules look totally identical, they form inclusion complexes of slightly different stabilities when they hit the cyclodextrin. The instrument catches these tiny differences in stability, allowing chemists to successfully separate the bad molecules from the good ones. Brilliant, right? Okay, on to Case File 3. Tracing environmental pollutants. This covers trace and residue analysis in environmental chemistry. Moving from the tightly controlled pharmacy out into the massive chaotic outdoors, the instruments hunting for dangerous pollutants have to operate at ultra-trace levels. We're talking parts per trillion. To even wrap your head around the mind-boggling scale of that analytical power, just imagine trying to find a single drop of a toxic substance hidden perfectly inside 20 Olympic-sized swimming pools. That is the exact needle in the haystack these instruments are tasked with finding to protect our environment. To actually pull off this impossible task, high-resolution mass spectrometry acts like an environmental sniper. By using a procedure called selected ion monitoring, or SIM, the mass spectrometer is tuned to a massive resolving power, typically around 10,000. It literally adjusts to dwell specifically on the peak tops of targeted analyte ions. By doing this, it minimizes interference from other natural substances, which allows chemists to confidently identify and quantify incredibly dangerous pollutants, like chlorinated dioxins, even when they're buried deep in complex mixtures of mud, sediment, and surface water.
Finally, let's open Case File 4, Monitoring Chemotherapy, specifically monitoring the concentration of cytotoxic compounds.
Operating right beside a patient's hospital bed, these unseen chemical shields are managing some incredibly delicate medical procedures. When a patient is undergoing powerful chemotherapy, the levels of administered drugs in their body fluids require strict, constant monitoring. These cytotoxic compounds are designed to be toxic to cancer cells, obviously, but the line between an effective dose and a dangerous overdose is razor thin. In this environment, speed of analysis is absolutely crucial. Continuous, automated analytical procedures monitor the patient's body fluids, ensuring those chemo drugs remain at the exact right concentration to fight the cancer without overwhelming the patient's system.
So, let's wrap this all up. Our unseen chemical shield, bringing the case files together. Whether it's the food you eat, the environment you live in, or the life-saving medicine you take, analytical chemistry is a massive industry dedicated entirely to our collective well-being. It is this amazing, interlocking web of protection. From ensuring your milk is free of animal antibiotics, to confirming your therapeutic drugs are the correct, healing shape, to policing our waters for toxic traces, and even guarding a patient during chemotherapy. It's all connected.
I want to leave you with a final thought today and really challenge you to appreciate the hidden analytical science that makes our entire modern world possible. The very next time you open a bottle of water or take an over-the-counter medication, ask yourself, how many unseen chemical detectives armed with mass spectrometers and complex chromatography worked in the shadows just to guarantee your safety? It's a fascinating scientific reality and one we literally bet our lives on every single day. Thanks for joining me for this explainer, and keep questioning the science hidden inside the ordinary.